Matrix representation of graph. So there are two types of matrices we have discussed. One is adjacency matrix and the second is incidence matrix. So in adjacency matrix, we make a matrix of n by n order. That means number of vertices are n. So we make a matrix of order n by n. And for incidence matrix, we make a matrix of order n by n, where n is the vertices and m is the edges. And two types of problems we have discussed, that one is for directed graph, second is for directed graph. Now today we will discuss tree. So next topic, which is tree. So another part of the graph. So this is tree. Tree, the definition of tree is a cycle graph. A cycle graph is said to be a tree. A cycle means which doesn't make a loop or which doesn't make a circuit is said to be a tree. Or second definition, a connected graph which has no cycle. Connected graph which has no cycle is said to be a tree. So that means these are the examples of tree. Single vertices, that means with two vertices with one edge, three vertices with two edges. So these are the example of tree. So that means this one is not example. This make a circuit or which make a loop. That means this make a loop. This is not the example of tree. That means any graph which is in this form, having four vertices but making a circuit form. So this is not an example of tree. So these are the examples of a tree. So that means a cycle graph which doesn't make a cycle, or a connected graph with no cycle is said to be a tree. So these are the examples, several examples we have discussed here, that means related to the tree, but is are not the example of tree. Okay, which make a circuit or cycle, not an example of tree. Now, you know the tree, which is basically based on the tree which have leaves. So these are the leaves, but the leaves doesn't make a cycle. So another example, this example we are not also example of tree, because this make a circuit. This make a circuit. So this make a circuit. So this is not an example of tree. Not an example of tree. Okay. So these are the examples. That means these three we have crossed here. So these are not example of tree. Otherwise, all are the example of tree. This is tree. This is tree. All are trees. Now we define directed tree. So for defining directed tree, a directed tree is a cycle directed graph. So we have already discussed the directed graph. So if it has one node with in degree 1, while all other node will have in degree 1. So that means we all the nodes in degree nodes with have degree 1 is called directed tree. So that is gives us a direction. So that means this is the example of directed tree, which is doesn't make a cycle and follow the tree. A tree is said to be a directed tree. So that means which is a cycle directed graph. So it doesn't make a cycle, but having a direction is said to be the directed tree. Simple example you can choose as, that means this is the example of a simple tree. But we provide this a direction, so this is the example of directed tree. So same as we have three vertices, that means this type of vertices. So this is the undirected tree, but when we provide as a direction, so this is the example of directed tree. Okay, so all these are the example of the directed tree, which have integrity 1. So you know that what is the integrity? Integrity means initial vertex have degree 1. So is integrity. Now, order tree. So order tree, if in a tree at each level an ordering defined, then such a tree is called ordering tree. So that means the order or the level of all the trees are defined. So that is called order tree. So initially, when we see the plant, so first we see the root. So the root, that means initial vertex. Initial vertex is known as the root. So initial vertex known as the root, and others are said to be the leaf. Okay, So these are the roots, and others are the examples of leaves. So there are several that means leaves maybe have happened. So you see that there are two examples we have discussed here. So the initial vertex is known as the root, and other, that means we calculate the order. So what is the order? Both have different order. So that means how to check the order? So number of levels. So levels. So that means how many levels are there? So this is the initial tree one. So here having two leaves. That means this is known also known as the children of this node A, B or C, and B and C having two nodes. And similarly B and this G having two nodes, H and I having only one children, that is known as the J. So these are the leaves. And similarly for this case, that means same question, same graph. There is no difference between these two graphs, but the difference is that means we choose only different vertex. So in place of D, here we use D, vertex D, but here we use the vertex E. Okay. So just we count how many roots are there. So that we which have only one child. So these are the examples. Now we move to the rooted tree. So what do you mean by rooted tree? If any a directed or undirected graph, undirected tree has exactly one node or vertex is called root, whose incoming degree is 0. That means initial vertex, that is called the tree. So whose incoming degree, that means incoming degree means in degree. In degree is 0, that is called the root. And all other vertices having incoming degree 1, that tree is called rooted tree. So this is the initial vertex, and this have incoming degree 0. That means there is no previous vertex there. So that means A is the initial vertex. So that is called the root of the tree, and other vertex having degree 1. So you check the other vertex having degree 1. So the degree of this vertex B is 1, degree of vertex C is 1, D and E is also 1. So that means a tree with no node is called rooted tree. That means empty tree. So simply you can take an example, empty tree. So a single node which have no children is called the rooted tree. Okay. Okay, so this is the example of rooted tree. Now we move to the forest. So what is the forest? If the root and corresponding edges, root that means initial tree, and corresponding edges, these are the corresponding edges connecting the nodes are deleted from a tree. So that means when we delete these edges from the tree, okay, this one, Kumar, okay. So directed or undirected tree, that means having exactly one node. So that means there is no previous node, that is called the root. That means you can take simple example of plant. Initially, the plant having root, then Okay. So for forest, that means any tree is given. So that means if the root, this is the root, and this have corresponding edges. So these are the some edges, and we delete the edges. We delete the edges from the this tree. So then we make the this type of graph. So that means the disjoint. So the disjoint tree is known as the forest. So this is known as the forest. Okay, so this is known as the forest. Okay, so this is the rotatory. That means this is the forest. So just we remove all the edges from the rooted tree, that means or from the tree. So this is known as the forest. So that means this is also part of the disconnected tree. Now we move to the binary tree. So what is the binary tree? So if the out degree of every node is less than or equal to 2 in a directed tree, so then the tree is called a binary tree. So that means first is the root. That means this having two children. So this is called a left child and right child. And corresponding this is also root of which tree, which what is it? That will D or E. That means root means this is a father. A is the father, and who have two childs, B and C. So B is called left child, C is called right child. Again, so that may be extend the family, extend the family. So B is work as a father. Okay, so B is father. Then the who have two child also. D and E be two childs of B. And same with C is a father. Then this is the root of both F and G. And B is the root of both D and E. And A is called, what is the A of D and E, F and G? So they are the ancestors. Okay. So this is left child, right child, and similarly for the this is also left child of B, and this is the right child of B. So this is right child of B, this is left child of C, and this is the right child of C. Okay, so this is the binary tree. Binary tree means maybe some having only one child, but binary, that means every root divided into two parts. So that means having left child and right child. So left child and right child. So be the example of binary tree. So simple, maybe any parents, that this is the parent and having two children. One, this is called left child and the other is called right child. Now we move to the basic terminology, that means basic definitions of root. So what is the root? A binary tree have a unique node. That means when we start our graph, so graph or tree, so we start, so we choose any vertex, then we draw this thing, we draw this thing, we draw this maybe. So the root, so this is called the root, that means initial vertex. So when we start our journey, that means we went draw any graph. Graph is also a tree. A tree is also a graph, but a cycle graph. A cycle graph it doesn't make a cycle. Okay, so left child. So the node to the left of the root. So node to the left of the root. So this is left of the root is called the left child. Node to the right of the root is called right child. So left child and right child. So node to the right of the root is called the right child and left of the root is known as the left child. Now, parents. Who is the parents? So the node. The node having left child or a right child or both. Left child or right child or a both is called the parent of the node. So that means only left child. Suppose this is the root. So this is called the parent. So this have only one child. So this is the child. That means this is the left child, and this is also called the parent. Root is also called parent. Which may be that means in this form that we having both two children, uh, two child. So that means this is the parent, so having left child and right child. So maybe having left child or maybe right child or both child is called the parent of the node. So parent of the particular node. So that means suppose for this example, this work as a parent. Parent of which child? That means in this child. So that means suppose this is the vertex A, B, C, D. D vertex. So E and F having two childs. That means D having two child E and F. So this child doesn't have any further. So that means when we make another, that may extend this tree. So that means E is the father, then E having father of two child. So that means F, G and H or etc. So these are the sibling. Now next definition is sibling. So two nodes having same parent are called sibling. So you know that means this is the root or this is the parent. So left child and right child, these two are the siblings. So these two are the siblings of the, that means root tree. So that means having same parent, so are the siblings. So that means same, for example, this and this having this are the siblings of having same parent E. Okay, so leaf. What is the leaf? So a node with no children, a node with no children is called the leaf. So the number of leaves in a binary tree can vary from one minimum to half of the number of vertices maximum in a tree. So a node with no children is called the leaf. So that means next, the ancestors. So if a node is the parent of another node, then this is called the ancestor of the node. So that means having two child, and these are the parent of this one. So this is called the ancestors. Ancestors of these two childs, left and right child. So this is left and right. So this is the ancestor of these left and right side for this these two, for these two. So this is the ancestor, descendant. So a node is called a descendant of another node if it is the child of the node or child of the some other descendant of the node. So that means child of the node. So this is, suppose this is the L with the child of the node, and suppose R having two children, are having two children. So that means so the node L, that we here we give the name of this node and we give provide the name of this node. So are the descendants, are the descendants. Now, for example, we take an example. In this example, we can find all these things. So this is the example. Note down this example. So for the tree, So we provide the level. So this is the level 1, that means the primary level. This is called the root, and this is the level 2, level 1. This is level 2, that we having two child, and this is the level 3. So that means this is the level 3. D, E, F is on level 3, and G, H, I, J, and K. This is the level 4, and this is the level 5. L or M with the level 5. So note down this one. Level 3, level 4, level 5. So level 5 only having this one node, L or M. Other are having level 4. So we already write level 1 means initial node, that is called root, having two child B and C. So this is the second level, because B and C also having the child. And for after B or C, that means here is D and E, or there is F. So this is also on the level 3, F having only one child, which is K. Okay. Okay. So all you all noted this graph, that means this tree. Now we start with the list of children of each node. List of children. So we write the node. We write all the nodes A, B, C, D, E, F, and K, because G, H, I, J doesn't have any children. G, H, I, J doesn't have any children. So we write all those nodes which have the children. That means, so A having children, children of A is B, C, B having children, children of B is D, E, D having children, children of D and D is G and H, E having children, I and J. So C having only one child, F having one child, K having two children, L and M. So those having children we write as node. So A, B, C, D, E, F, and K. We write the name of the children. So you can easily write the name of the children. Okay. So A having two children, B, C, B having two children, D, E, C having two children, only one child, F, and D having two child, G, H, and E having I, J, and F having only one child, K, and K having two child, L and M. K having two child, L and M. Okay. So K having two child, this is L and M. G, H, I, J, K, L, M doesn't have any child, so we stop here. Okay. So node, we write node those who have child. Now, same question. We write the siblings. So list of siblings. So siblings, you can list the siblings. So here B and C be the sibling, BC be the sibling, DE be the sibling, and GH be the sibling, IJ be the sibling, and LM be the sibling. Okay. So BC, DE, GH, BC, DE, GH, IJ, IJ, LM. So these are the siblings. So that means BC sibling, DE sibling, GH sibling, IJ sibling, LM sibling. So these are the siblings. Now find the depth of each node. So depth means level. So we check the level of each node. So we already write here the level 1, 2, 3, 4, 5. There are 5 level in this tree. Just we write here the level. So A, level of A, that means initial node is having depth 1, BC having level 2, DEF having level 3, GHIJK having level 4, and LM having level 5. Okay, just we write the level. So when you want to write, that means left side and right side of each node, so you can write the left side and right side of it, and the correspondingly ancestors you can calculate. That means write the ancestors of nodes. Okay. Now we move to the next topic, which is minimum spanning tree. So that means these are two important topics, and we have two algorithms: Prim's algorithm and Pascal algorithm. So first we understand the spanning tree, then we understand the minimum spanning tree. So we move to the spanning tree and minimum spanning tree. So first we define spanning tree. So let G be any graph, G be any graph, and T be any subgraph of G. T be any subgraph of G. So then T is called a spanning tree. T is called a spanning tree if T is a tree. T is a tree and T have every vertex of a graph G. T have every vertex of a graph G. That means vertex of G is equal to vertex of T. So then T is called the spanning tree of the graph. For example, we have five vertices in the graph G: V1, V2, V3, V4, V5. So all these five vertices we also appear in the tree. That means V1, V2, V3, V4, and V5. But which makes a tree. That means doesn't make any cycle or circuit. So it doesn't make a cycle because T is a tree. So we write here that means T is a tree. So T is a tree means a cycle graph is said to be a tree. So tree, and all the vertices of graph G is equal to vertices of tree. So it's called the spanning tree. So this is an example of spanning tree. Example of spanning tree. So that means subgraph, be also the subgraph. So that means any portion we can choose of any graph. So we also the example of subgraph. So subgraph means this is the subgraph of graph G. So these are also example of tree. What is the basic difference between subgraph? Subgraph means we can take any portion of the graph. So we already defined subgraph. So this is a subgraph of graph G. V1, V2, and V5. So this is a subgraph of this graph G. But this is not a spanning tree because it make a cycle. This is not a spanning tree, not a spanning tree. A spanning tree require two situations. One is this is a tree. Second is this cover all the vertices of graph G. This cover all the vertices of graph G. Suppose you graph or you say this is the spanning tree. This is not a spanning tree because this cover only three vertices. This cover only three vertices. V3, V2, V1 or V5. V3, V4 doesn't cover. So that means for a spanning tree, it should cover all these vertices of graph G. It should cover all the vertices of graph G. So a spanning tree is defined only for a connected graph. So any connected graph is given, so then we can define a spanning tree. So the collection of trees is called the forest. So that means when we collect all the trees, these are the example of forest. So every connected graph has at least one spanning tree. So we can take any example. What do you mean by connected graph? You know, we have already defined connected graph. So have at least one spanning tree. So these are the examples which contain at least one spanning tree. So this graph having two components, component 1 and component 2. Now we go to the minimal spanning tree. So G be any weighted graph. So over here any graph that we edge having some weight. So a spanning tree of G is called a minimum spanning tree. Is called a minimum spanning tree if it has minimum weight. It has minimum weight. So the weight of a spanning tree T of the graph G is defined as the sum of the weight of all branches of T. That means we do the sum of all weight of the branches of tree. That means any graph is given. When the graph first the graph is converted into a tree, is minimum spanning tree. That means spanning tree, and we add all the weights of each vertices. That each branch means each edge. So that is known as the minimum spanning tree. So this minimum spanning tree is also called the shortest spanning tree. So there are two powerful algorithms for finding the minimum spanning tree. One is Prim's algorithm, second is Kruskal algorithm. So there are two powerful algorithms minimum for finding minimum spanning tree. So Kruskal algorithm and Prim's algorithm. So for Kruskal algorithm, so in this algorithm, first we choose an edge of the smallest weight, which has no loop, which has. After that, we choose the next edge, which have smallest weight among the remaining edges, and make no cycle. And we proceed this again and again until n minus 1 edges of graph G is selected. So then we get a minimum spanning tree. So this is the algorithm. So how to proceed to obtain a minimum spanning tree of any connected graph. So for example, at least one example is given. Determine the minimum spanning tree of the weighted graph. So this is the weighted graph. So here we obtained the minimum spanning tree of this weighted graph. So each edge having some weight. So the weights are given as here. So on the basis of this algorithm, so we process step by step. So that we first we write all the edges with their weight in increasing order. With their weight in increasing order. So we write all the edges. Increasing order means having smallest weight is BC. BC having weight 2 and ED also having weight 2. So we write BC, ED. Then we write next is AD. AD having weight 3. AD having weight 3. Then we write CD. CD having weight 4. Then we write AB having weight AF having weight 4 and AB having weight 5 and EF having weight 5. So we write all these pair of vertices and CF having weight 6. So CF, yes, CF having weight 6. So we write all the edges and corresponding weights. Now we choose the pair of vertices which have a smallest edge, which have a smallest weight. So that means when we choose BC, there are two options here. So one you can choose BC or second you can choose ED. So BC and ED. So that means when we choose BC. So when we choose BC, so then second necessary we choose ED. But BC cannot connect directly to ED because BC is here and ED is here. So we choose the pair of vertices in this way. So we can connect the next selecting pair of vertices. We connect the next selecting pair of vertices by any of the used vertices. Okay. So here we cannot select BC. So we choose ED. So we choose ED. So ED also because having same weight, so we can choose ED. So next we have AD. So that means ED and AD. So we can select them. So ED and AD. So this is ED. So next minimum weight is 3. So ED and AD. So we can join next pair of vertices by previously used pair of vertices. That means DAD. So we can select this one. Because when we choose BC, so BC cannot join to AD. So because we write BC here, BC and AD. So AD, the position of AD in the graph, position of AD. Position of AD in the graph is this. So position of AD in the graph is this. So position of AD in the graph is this. So this is not a proper way to select such a type of edges. So we choose on this way, that which we can join next pair of vertices by previous one. Okay. So next, let me CD and AF, which having same weight. So CD, so we can join D already have, so we can join with D. So CD, we can join with CD. Yes. So now next minimum is AF. AF have same weight, so we can join AF. So yes, we can join AF. So this is AF, and because we remember this thing also, we choose in this way, which doesn't make a cycle, which doesn't make a cycle or a loop. We choosing the pair of vertices in this way, and we also and next is AB. AB having minimum weight, so AB. So we have possibility to choose AB. So this is the AB. So AB positions we check from the given graph, and we see that we have selected all the required vertices in the graph. That means we have 6 vertices in the graph G, so we have chooses all the vertices of the graph G and make a spanning tree, and we write the weight. So we add all the weights by using all the trees, which is 18. So there is no need to choose this one because this make a cycle. EF, when we join EF, then make a cycle. So this is the spanning tree. So that means this is the Kruskal algorithm. Okay. Okay, students. So thank you. Now you can leave the session.